One.
So we're doing the school bus routing problem. We are the group Big Yellow School Buses. In our problem, the graph represents a street map for a school district. Each vertice has the number of children present at that vertice. Each bus has a total carrying capacity and the maximum distance it can travel, with it starting at the school and returning to the school once it has picked up the children. The goal is to have the minimum number of school buses used. Now, this is our graph. This is the school. As you can see, the edges are labeled with the distance, and the vertices have the children at them. The vertices themselves have the number of children present at that vertice. In this particular example, the max distance that a school bus can travel is 20, and the seat capacity for that school bus is 10. Again, the goal is to have the minimum number of school buses. So a possible route would be to go from the school to here, from that vertice, once you've picked up the 6 children, to here, get the other 4, and then go back to the school. You then have those children picked up. You can have another route from here, pick up these children, and return. Now, for this, you picked up the maximum carrying capacity of 10 children. You also kept under the maximum distance with the 4, the 3, and then the 5 here, coming to a max distance of 12, or distance of 12. And then for this one, you had 7, 3, and 3, distance of 13, with the carrying capacity only getting up to 8. So in this scenario, this would be the optimum solution with 2 school buses. However, this is an easy example.
What makes the school bus routing problem a combinatorial optimization problem is that it has certain constraints that need to be satisfied, and this school bus routing problem can be minimized to a certain extent. In our case, we're looking for a set of finite number of states or tours that can pick up the number of students given the certain constraints in this problem, which are the distance that a school bus can travel and the capacity that the school bus can hold for the number of students. The different tours can be compared using the differing number of buses, where the minimum number of buses would be our most optimal solution. And with that sense, the school bus routing problem can be optimized, but only to a certain extent, as we have a decision version that you can route the graph with a set number of buses. So given a certain minimum number of buses, could you meet that satisfaction? Or the optimization version, where you can use just the overall least number of buses. But currently, determining the optimum solution or the candidate solution for the school bus routing problem is an NP-hard problem, which means that there currently exists no polynomial time solution that will give an optimal solution.
So we're going to be discussing how you can solve the school bus routing problem with a polynomial time solution. This is based off of what we've already learned before with the greedy algorithm. We're going to be using swaps, and we're going to be using it in a state space search. So as we've already discussed, that there's a finite number of states that are possible. These states will be the number of tours. So for instance, here is a state. It corresponds to this graph here. It corresponds to going to visit A, then D, then C, then B. The way this works is you begin with, this is just a visual representation, you begin with something like an array where it would check the first node with a bus. We'd start with one bus. It would go to that node from school. That'll take 3 distance. It'll then go to the next node here, so long as it doesn't violate 2 things, which we have already stated here, which is a capacity of 10 and a distance max of 20. So it doesn't violate the distance max, so you may go to this node. However, this would have too many children. You would have 6 plus 5 children. That is beyond the capacity of a bus, so this would require a secondary bus in truth. So that means right here in our graph, we already have 1 bus. Now there is a second bus that we are using, so we have to go straight to D. From D we would go to C, which we can do. There's 3 children there, and there is only a space of 3. So you may go to there. However, you cannot go to B because that has 4 children. 3 plus 5 plus 4 would be beyond the scope of a bus, so that simply must return back. So now we have 2 buses, and then finally we have the third bus. So this leads us to a conclusion that there are only 3 buses. However, this is only one of the states that we have possible, and what we're going to do is we're going to use an application of the greedy algorithm where we're trying to minimize it by making swaps and selecting swaps which result in a lower cost, aka the lower number of buses. You can do that in this situation simply by switching D and B. If in this situation you switch the orders of merely these 2 nodes, I'm just going to erase this to make it a little clearer. If you simply switched D and B, you would have A, B, C, D. Very high level math we're talking about. So, in this situation, I'll use green to make it a little easier to see. You can go to A. Because it doesn't violate the number of distance, 5 and 3, this is not greater than 20. 5, 3, 3 is not greater than 20 either. And it doesn't violate the capacity of 10. 6 plus 4 is 10, so you are within capacity. You can go to both of these nodes and then return to the school. That would mean that this takes only 1 bus right here. Then for C and D, you may simply, we've already effectively proved this, but I will go again. This has only a distance of 3, a cost of 3. This is only a distance of 3 and a cost of 5. And you may return home using only 8 capacity. So this would result in only 2 buses being used, which is the optimum. However, not all problems are this simple. Because we are using a greedy algorithm, it is impossible for us to get to the global maximum every time. We may result in it, but more often than not, we are going to end up with a local minimum. So over here, I have a situation in which it is impossible given this ordering. In this ordering, it would require, I believe, 3 buses in order to reach the end. You have your trip from D to, you have your first trip to D, then you have your next trip to F, then you would have your next trip to B, and then you would have to return back. That would give you, D, as we have listed here, has 5 children, F has 1 child, and B has 1 child. It is that would result in 7 children being picked up. However, you can't reach C because C has 5 children, which would go over your capacity. So that would require this to be 1 bus. However, C and E, C has a capacity of 2. C has a number of students of 5. E has a number of students of 2. So you may go from C to E. However, you cannot reach A because A has 6 students. So you must return back to your base. Finally, we have A, which is all by itself, which results in going there and back, which results overall in 3 buses. So to try to simplify this, we must try to swap. However, by looking at this, we only swap in the condition that we can reduce the number of buses. The only way to reduce the number of buses in this particular alignment would be to swap 2 nodes, which would be to swap F and to swap C. However, this would violate the distance, which we have already placed as 20. Because in this situation, I will now use green to elaborate. If you would switch these 2 nodes and ended up with a pattern of D, C, B, F, E, A, you can go to D to C. Simply D to C, and then return back. That would take 1 bus. However, you cannot go from B to F to E, because to get to B, it requires 3. To get to B to F, that requires an extra 3. To get to F to E, that requires an extra 3, that is already 9. Then finally, to get to A, you will have to traverse 10, and the only way to return to the school would be with this 3, which would make the total cost of the trip 22, which is not allowed. So you cannot allow this swap, therefore we would end up only with a local maxima of 3 buses. So the real optimal in this case is the pattern A, E, B, F, D, C. In this case, you can go, starting from the school, to A at a cost of 3, and you're able to pick up 6 children. You're able to go to A to E, which is a cost of 10, and still be able to pick up 2 children. You can go from E to F, and you can go to F to B and back to the school. So this is the only possible way of encompassing 4 nodes as 1 bus. And the last two, D and C, we've already proved you can go to, and that would result overall a cost of 2 buses. So as we have shown, this is only an approximation. You cannot truly reach the optimal in this way, as you couldn't with any algorithm, at least proven so far. So in this case, we would be